9? Okay. And did anybody calculate the percent abundances for all of them? You did all of them? Did it add up to 100%? It did? Oh, good. And let's just review some of this stuff here. We do this. What you want to do is, and this is something I do, is when you watch somebody do a calculation or somebody else does a calculation, you want to see if you can repeat the same calculation yourself. And since you have already done the calculation, no one in the morning class did the calculation. Let me talk about it here. I'll just go through these notes here to save a little bit of time. But how did you do that? Well, one person I recall last week told me that what they did was they summed all 3 of these percentages and then divided by 3. In other words, they just took the average of the percentages. And that's something worth trying because you get the correct units. If you just go ahead and take the abundance of H1, which is 99.9885, and then take the abundance of this other H1, which is 99.9885, and the oxygen, which is 99.757, and add them together and divide by 3, it comes out as a percentage. Well, what happens is when you try to combine at the end all of the percentages generated for all 9 possible water molecules, it doesn't add up to 100%. And so there's for sure something wrong with that. And so that's one way you could have figured out it was incorrect. But this way does work. And one thing you might try is you might try to do 99.9885% times 99.9885% times 99.757%. And what units would you end up with there? Yeah, you'd end up with percent cube. And does percent cube have any physical meaning? No. There's no meaning to that. And so let me see if I could get this. Working here. Yeah, so all 3 of these multiplied together will give you the units of percent cubed. And that's not going to work because that has no meaning. However, we should leave one of these percents there. This is like a composite unit that we've already been dealing with. So if we leave one of these percents there, let's say the O16, it doesn't matter which one, but we'll leave the O16 here. And then we got to get rid of this percent squared. So how can we go from a percent to something else? Well, one way we can go from a percent to something else is go from a percent to a fraction or a percent to a decimal. And going to a fraction or decimal doesn't matter. Either one works. And so what we need to do is we need to get rid of this percent squared. And the way we're going to get rid of it is just convert this. And so I'll convert it from percent to a fraction. I can reconvert it back to a percent by multiplying it by 100%. The hundreds cancel, leaving you a percent. But it says the same thing. And then do the same thing for this. So now I have a fraction which is dimensionless. The units would cancel. This one also. And then I have percent here. So fraction times fraction times percent gives us percent. If I made a mistake in an earlier calculation, if you make a mistake in the calculation, just cross it out. I made 2 mistakes, and then just rewrite it here. And so this is what we do in lab. Just cross it out and rewrite it. We don't erase it because we write our observations using ink. And if I did this in pencil, yeah, it'd be easy to erase, but pencil isn't as permanent as ink, and so we try to record all our observations. Now, this makes sense as well. And so the way we think about this equation here, let me highlight here, since it's kind of mixed up. So the way we think about this calculation here, oops, is like this. So I have 99.757% abundance of oxygen 16. So out of that 99.757% abundance of oxygen 16, what fraction of those molecules will have H1 on the left here, the first atom I picked? And the fraction that's going to have H1 is 99.9885. In other words, if I had, let's say I had 100,000, or actually a million. If I had a million hydrogens, then there's going to be a 99,985, 999,885 chance I'm going to pull out the H1 versus the H2. The H2 will be only 115 out of a million. And so, anyway, so that's the fraction that I'm going to have for H1. Now, what about the second H? The second H is going to be 1 with a 99, or actually I should say 99.9885% chance. And so we convert that into fraction of this percentage. So out of this percentage of oxygen 16, what fraction will have H1 on the left, what fraction will have H1 on the right, and this is going to give us a percentage here. So this makes sense as well. You know, versus if I thought about just adding the percentages here and then dividing by 3 to get the average, it doesn't quite make physical sense, but this makes more physical sense. And then, okay, this is the percent that I have of oxygen 16, and then I look at the other possibilities. Another possibility is, rather than H1 here, I have an H2. Well, what fraction will be H2? Out of that million, only 115 will be H2, so that would be a 0.015, 115, excuse me, out of 100. Does that make sense? All right. And so we're looking at what fraction of this percentage. Okay, once I finish the oxygen 16s, I'll have all of them, and all the oxygen 16s will total up to this percentage, because we're looking at the fractional abundances of this particular percentage. And then I go to oxygen 17, then I go to oxygen 18. So if I take the oxygen 16 with all the variations, oxygen 17 with all the variations, and oxygen 18 with all the variations, add those up, that's going to add up to 100%. So we want to do that for all of them, just to verify. Now, when I do that, I carry a lot of extra decimal places here to avoid round-off error. So let's say I decide to round this off to 100. Then obviously the percentages aren't going to add up. You know, if I go 99.7 is close enough to 100. You know. Even if I go 99.7 and then drop these and then add everything else, it's not going to quite add up to 100. So for something like this, you want to add more decimal places. All right, so we want to know what percent abundant. This is going to be the most abundant. And so if I had a million water molecules, 997, or no, 100,000 water molecules. So 100,000 because I'll just move the decimal 3 over. And so that would be 99,000. So 100,000, out of 100,000 water molecules, 99,734 will be H1, O16, H1. Then how much do those weigh? Well, how much does an H1, O16, H1 weigh? Some people will say, well, H2O molecule weighs 18.02. You know, because hydrogen weighs 1.00794 and oxygen weighs 15.9994, add those up, and we're going to get 18.02. But this is the average water molecule. And a weird thing happens, if I had a million water molecules, do any of them weigh 18.02 U? It turns out none of them weigh 18.02. I'm going to have a water molecule here, H1O16, H1, that weighs 18.01 U. So it weighs slightly less. than the average. And that makes sense because this is the lightest water molecule, and all the other water molecules are heavier. But when we look at the average is very close to this. I mean, it's just slightly heavier, the average. It's slightly heavier because 99.7% of the water molecules are this one. So it's going to be a weighted average. Okay, does that make sense? Okay, then you repeat this. And so I'll just use these since I already wrote these earlier. This is just some additional calculation. Here, the average hydrogen weighs 1.0794 U. I didn't do this, but do you remember doing something like this? To figure out the mass of an average hydrogen atom, we take the natural abundance, either decimal or fractional abundance of H1. H1 weighs 1.007825. And then the fractional or decimal abundance of H2 times the mass of H2, which weighs 2.014102 U, and then we end up with 1.00794. Now, because of the definition of the blank, we could use either units here. So for example, if I have 18.02, the two units that I can associate with this number are U per molecule, or atomic mass units per molecule, or grams per mole of molecules. And this numerical equivalence of these two units is due to the way the blank is defined. What was the definition that made these numerically equivalent? The definition of the mole. Because the way we define the mole, we can use either. And therefore, a lot of times when you see the mass like this, it's just written 1802. It says written 1802 because you can tag it with either unit you want. That is U per particle or grams per mole of particles. And the particles in this case are the molecules. And the same thing here. The average mass of a hydrogen atom is 1.00794. That's what's going to be on the periodic table. And again, this is going to be U per hydrogen atom, or grams per mole of average hydrogen atom. I wrote average because there's no hydrogen atom in nature that exists that weighs this amount. You know, the hydrogen atoms are either going to weigh 1.007825 or 2.014102. Okay, so that's what I'm doing on this slide. Actually, I'm just going to use this PowerPoint here to save some writing. So if we do this for the next most abundant, I don't know if this is the next most abundant. I'm just guessing that this is the next most abundant. And so we could try this. Rather than grabbing H1, let's grab an H2. Grabbing an H2 is much more difficult because there's only 115 of those in a million hydrogen atoms. But let's say we grab that. Okay, so we grab an H2, we have an O16, and then an H1. H1 is likely. And so we do the same thing. What is the percent abundance of this? So over here we'll have the fractional abundance of H2. Fractional abundance would be 0.0115%. Excuse me, that's a percent. And then converted into fraction, 0.0115 out of 100. Now I'm going to move the decimal over here 4 places, and that gives me 115. And then move this 4 places over, so this would be 10 to the 6th. So 115 out of a million. So that's 115 parts per million. Of the hydrogens will be H2. And then over here, 999,885 out of a million will be H1. And then we have our O16 at 99.757. So out of this 99.757% O16, what fraction will have H2 and H1? And so we do the calculation here. We get the correct units. It's going to be percent. And then we're allowed, how many sig figs here? 5 sig figs?
Is that correct?
Well, it's due to this one. How many sig figs here?
3.
3. And this is multiplication, therefore we're only allowed 3 sig figs. But I'd like you to carry a fourth, because I want you to show me how you round this. And so I'm going to go from percent to fraction here, and then round it. And so it's 0.0115 out of 100. 0.0115 out of 100. I move this 4 over, I move this 4 over, so that's 115 out of a million. Slightly less than 115 out of a million. Yeah. Because this was 115, this is 114.7. Okay. This is a very small percentage. And so this one is going to be a lot rarer. This one's going to weigh more too. So the H2 weighs 2.014102. The O16, 15.994915. The H1, 1.007825. So I combine these and I get 19.016842. So this one is heavier than the last one by 1 U approximately. And this is going to be heavier than the average water molecule. And the units, we can either do U per H2O16 H1 molecule, and so U per particle, or grams per mole of particles. And the particles here would be H2O16 H1 molecules. So this is just a repeat of the previous calculation. Are you okay with this? So now we're going to generate the ideal mass spectrum. At least start generating the ideal mass spectrum. So ignore this purple for right now. The mass spectrum is the output from the mass spectrometer. This is ideal because sometimes what happens is when you try to ionize the molecules, they break apart into fragments. But we're going to assume that we didn't break apart any molecules, that they're all intact. And we feed the molecules in the mass spectrometer. The lightest molecule is going to hit here, because the lightest one is going to be the most deflected. And so it's going to hit here on our detector. And it's going to generate a peak. And if we write on the Y scale here, the percent, then this peak is going to be 99.734% in intensity, amplitude. And the mass here that it hits is going to be at 18.010565 U, right there. On the mass spectrums in the book, they'll just write like 18. It's just a hair above 18. But here we can get the mass to 6 decimal places. All right. Then at a slightly heavier mass, this is 18. At a slightly heavier mass, we're going to have 19.016842 U. And we'll get a small peak, this black one here. That small peak, the black one, is going to be 0.0115%. And so we're going to have 0.0115% H1O16 H2. Did I do that right, or did I get it backwards? No, H2O16 H1. Why does it make a difference? Let me flip that.
I don't think it makes a difference because you have both. You have forwards and backwards.
Yeah, it doesn't make a difference, but I just want to be consistent in the ones that I'm. Because the one we just calculated was for H2 O16 H1. Ultimately, it doesn't make a difference, but there are 2 ways of making this. And so the 2 ways of making this are I could grab an H2 first, followed by the H1, or I could grab an H1 first, followed by the H2. Do you see that there are 2 different ways of making the same molecule? So your first grab can be an H2, or your first grab can be an H1. If your first grab is an H2, then your second grab has got to be an H1 to make this molecule. And if your first grab is an H1, then the second grab has got to be an H2. Does that make sense? Now in nature, what's happening are just random collisions. As these random collisions happen, then there are actually 2 ways of making this. But the thing is, are they going to weigh a different amount? Are both of these going to weigh the same, 19.016842? And the answer is yes. I mean, is just flipped. They're both going to weigh the same. So what's going to happen is there are two ways of making this. And when we look at the calculation here, and I look at this expression here, if I flip these, that is, let's say I draw the H1 first. Well, that's 99.9885. That goes first out of 100. And then I draw the H2 first. That's 0.0115. So if I reverse the order of these, well, is that going to change this? The answer? No. I'm going to get the same thing. And so what I have to do is I have to compensate for this in order for this to add up to 100%. And so the compensation comes here. I'm going to have the original one I just calculated, which is this one, where I grab the H2 first, followed by the H1. And then I have to figure out the other way of making this is grab the H1 first, followed by the H2. Or in other words, I have a left and a right. So on the left, it can be either H1 or H2. Because of this, I need to double the probability. And so the probability, or in other words, the peak percentage, or the intensity of this peak is going to be 0.0. So 115 double is going to give us 230. So 0.0230% total. And so that would be the peak height here. Okay, then we're going to have 9 peaks here. And so what I want to do is I want to get the lightest and the heaviest and border everything. What's going to be the heaviest water molecule? H2O 18 H2. So can you calculate the percent abundance of H2O 18 H2? And the mass since and let me do a roll check here. Okay, Rommel? Rommel? Okay. Charles? Charles? Let me know when you have it. Actually, you have it. What did you get? Yeah.
I got, for H2, O18 H2, it's 2.7111 times 10 to the negative 9. And then the mass is like 22.0274.
Okay. These are some numbers that came up earlier. Some people got 1.32 times 10 to the minus 6, 3.60 times 10 to the minus 9, but 2.71 times 10 to the minus 9% should be correct. And we can't be as precise on this one because of how many sig figs is in the abundance of H2. Here, we only have 3 sig figs here. And so that's going to limit our precision. Now the mass, we can be more precise because the masses are known to 6 decimal places. So this is the mass that people calculated this morning, 22.027364 U. So see if you're getting the same. Just make sure you're getting the same. And then Sydney? Soha? Mona? Ty? Jackie? Jackie? Is that what you guys are getting? Those numbers? Do you need more time? Elmer? Shane? Kat? Kiana? Nikki? So as far as the percent abundance goes, we would do this. We convert this to fractional. So 0.0115 out of 100 are going to be the left hydrogen, which would be H2. And then the right hydrogen would be 0.0115 out of 100. And then the oxygen has a fairly low percentage, 0.205. And so we leave this one as a percent. So fraction times a fraction times a percent. You get 2.71 times 10 to the minus 9%. Is that what you guys got? All right. As far as the mass goes, here we can be pretty precise. We have 6 decimal places. The 6 big rules for addition are we just maintain the same number of decimal places. So it'd be 2 of these. It's going to weigh 4.028, etc. And then 1 of these, which weighs 17.99160 U, or grams. And we end up with this. 22.027364 U. And so this is going to be the peak furthest away. And so our lightest peak is going to be here. Our heaviest peak is going to be here. Our biggest peak is going to be here. Is this going to be the smallest peak here? Will this be the smallest peak? No. What will be the smallest peak? The smallest peak will be H2 combined with which oxygen? O17. So it's going to be H2, H2, and then O17. That's going to be the smallest peak. It's going to be quite small. But mass spectrometers are very sensitive. So we would be able to see that. Okay, in this way we can generate the entire mass spectrum. And so what we're doing is we're using that appendix D data to generate the mass spectrum of a molecule. The Appendix D data actually comes from the mass spectrum of atoms. So you shoot the atoms into the mass spectrometer, and then you see how many peaks there are. The number of peaks equals the number of isotopes. And then we can see how much each of those isotopes weigh to 6 decimal places at least, if not more. But we need to calibrate it. What can be used as a calibration standard for a mass spectrometer? Carbon-12, and how much does that weigh? Exactly 12 AMU. Right. Is it okay to move here to the next slide?
Do you think we'll still use that definition in 100, 200 years?
Do you think we'll still use what?
The definition of an AMU?
I would think so.
Really?
Yeah. I think oxygen 16 was a bit inconvenient. Even though there's plenty of oxygen in the air, there's other stuff in there. And I don't know, I guess it was easy to feed in there, into the mass spectrometer. I don't know why they changed it.
There just seems to be a trend towards more constant, well, that's a constant, but measurement definition is based on like physical constants.
Oh yeah, oh I see what you're saying.
So like about the
Yeah, yeah. Yeah. For example, length, yeah, and mass. The problem is you can do some more fundamental physics for this, but you know, what can you do? When you calibrate these things, let's say I calibrated at 12. If I calibrated at 12, is it still reading accurate at 100? At 200? And so normally when we do a calibration, we want the calibration to be close to where our readings are. That's to compensate for any drift in there. So we could calibrate it using the electron. You know, the cathode ray tube, electron weighs 0.005, dot, dot, dot. You know, there's a lot of digits, U. But, you know, that's getting further away. So the electron would be more fundamental because electrons in anything, you don't have to have carbon-12, you can have it whatever material you want. Spin electrons. But nowadays, we don't need carbon-12. I mean, if you know that hydrogen-1 is 1801.0565 that's enough. You could use this as a calibration standard now. All right, the question comes up, do I have to double this percentage? And so I have 2.71 times 10 minus 9%, H2O18H2. Should I double this like I did the last one? Are there two ways of making this or only one way of making this? There's only one way, so I'm not going to double this. The only time you double these is when you have this flip-flop thing that happens with the left hydrogen and the right hydrogen. All right, now what we're going to do is we're going to use some of these numbers here. Oh, this is one more. This is to show the other way of making this. This is a repeat calculation earlier, where it's like the commutative property of algebra. All right. So if I had 250 milliliters of water, a cup of water, let's say, a cup that I think is around 200. So we'll go to 250, quarter liter of water. How many of these the heaviest water molecules did you drink? You know, these weigh around 22 U, whereas normal oxygen weighs around 18 U. So how many of these molecules did you consume? And then what was the total mass of those molecules in atomic mass units? H2O18, H2, sorry. It's supposed to be O18. In U and in gram. So this would be a sample calculation using some dimensional analysis. So I want to know how much, if I drank a cup of water, how much of these heavy water molecules did I just consume in number and mass? So go ahead and give that calculation a go here.
Actually, it's 2.266 times 10 to the 14.
10 to the 14?
Yeah.
Okay.
I didn't convert the percent when I
Okay.
was doing the calculation.
Let's try. Let me fix that. Did anybody else get an answer? You got what he got? So we have 250 milliliters of water, and then we need to get rid of something that either gets rid of milliliters or milliliters of water. Actually, there is something that gets rid of milliliters of water. Do you know what we can convert that to? What? Grams. Because everybody should know the density of water. What's the density of water at 4 degrees Celsius? 1, pretty much 1. However, the further we veer from 4 degrees Celsius, the more it deviates. It goes down from 1 to about 0.96. And so we're going to say that this is close to room temperature. And so we'll just, if it's close, maybe we can go to 1.0 grams per milliliter. Now, what if I want more sig figs? Could I be more precise than this? Yeah. If this isn't precise enough, then what would we do? We would look it up in a density table. Density table will have a whole bunch of temperatures and then the density of water. Or we would solve for graphically using a chart, the density graph. Or we could use the law of density and temperature, which is an empirical equation. So we plug in the temperature and then solve it. But no temperature was specified. Since no temperature was specified, then in order to do that, we have to assume a temperature. If you're going to assume a temperature, which temperature would you most likely assume? What would be a reasonable temperature to assume? Like a glass of water sitting in your room. You'd probably just assume room temperature. And room temperature is what? 77 Fahrenheit, which is how many Celsius? Everybody should know room temperature in Celsius. 22 would be comfortable. This is uncomfortable. For me, it's uncomfortable. It's too warm. It's not 23. It's... Yeah, very close. No, this is an agreed upon room temperature. Obviously the room's going to be depending on what you set the AC to here.
Are they going to have to raise it over time to keep up with global warming? Committee on room temperature?
Yeah, maybe. Maybe now it's appropriate. So the temperature is going to be 25 degrees C.
That's hot.
It's hot, yeah. It's uncomfortable. For me, that's uncomfortable. Maybe they were already,
They're at the equator? I don't know why.
Yeah, maybe at the equator. So what we do is, if a temperature is not specified and we want something more precise, then we'll specify temperature. That's one option. Option two is you'd say, okay, the lab or my house runs from, or my room runs from this temperature to this temperature. So on the one hand, you would go to low. You know, what's the coldest? Maybe 18. What's the warmest? Maybe 25 or higher. And so what you do is you could do two calculations, at the lower limit and the upper limit. Have you ever done those type of calculations? But anyway, we're just going to go with this. You know, 1.0, it's not very quantitative, it's not very precise, but it would span a wider range of temperatures. And so we're just going to assume it's about 1.0 grams per milliliter. And so this is the approximate density. So the milliliters of water cancel. Okay, and now we have grams of water. And so try to figure out what to do next. Just take it one step at a time. So we want to get rid of grams or grams of water. And we do have something that gets rid of grams of water that we saw earlier. Does anybody recall what it is? Yeah. 1 mole of water, average water molecule, weighs how many grams? 18.02. So this is the average weight of a water molecule. And so grams of water cancel. That leaves us with moles of water. And then we can use the new definition of Avogadro's number, which is, exactly 6.022 times 10 to the 23rd water molecules. Per mole of water per mole of water molecules. And so moles of water cancel. That leaves me with the water molecules. These are your average water molecules. And then what can we do? Yeah, we're going to use the percent abundance. What was it? It was 2.71 times 10 to the minus 9%. Is that correct? H2O18 H2. Now we don't use a percent in dimensional analysis. What we're going to do is we're going to convert this into fractional form, because the fractional form will be our conversion factor. So I'm going to go from there to a fraction. And what this says is we have 2.71 times 10 to the minus 9 H2O18 H2 for every 100 H2O molecules. Well, that kind of doesn't make sense, does it? Or does it make sense? And can we have a fraction of a water molecule? A part of a water molecule? Like say 0.5 of a water molecule, 1/2? No. And so what I'm going to do is I'm going to convert it. I'm going to convert from fraction. Of course I can convert it back to a percent by multiplying by 100%. But I don't think percent is very useful at all either. And so what I'm going to do is I'm going to convert this into a part per billion. How do I convert this to a part per billion? How I convert this to a part per billion is I multiply it by 1 billion ppb. So if I multiply,
Parts per billion?
What's that?
We're using that rather than percent.
Um,
Oh, there's preference in there.
no, It's just to get it more, so you could visualize it more maybe. And so, in other words, if I do this, that's going to be 10 to the 9th times 10 to the negative 9th, which will give us 10 to the 0, divided by 10 squared, which will be 10 to the minus 2. And so this is going to come out to 0.0271 parts per billion. Is that very convenient? This isn't all that convenient either, because I can convert this from parts per billion back to fractional, and so this is going to be 0.0271 out of 1 billion. And so I'm going to have 0.0271 H2O18 H2 out of a billion H2O molecules. Well, since I can't have a part of water molecule, I'd like to get this in whole numbers. So what I'm going to do is I'm going to actually, maybe I won't. Let me go to parts per trillion. So to convert this to parts per trillion, I'm going to multiply by 1 trillion, or 10 to the 12th. And so this would be PPT. If I do that then and multiply it out, I'm going to get 27.1 parts per trillion H2O18 H2. All right, this makes a little bit more sense, but it doesn't matter. All these are the same. And so in other words, I'm going to have 27 H2O18 H2 for every 1 trillion water molecules. When I reconvert it back into a fractional. So to get rid of this 0.1, I'd probably do this. I just move the decimal 1 over. And so what I'd say is I'd have 271 H2O18 H2 molecules for every 10 trillion water molecules. Does that make sense?
Would you prefer me do it like that rather than just like dividing 2.71 times 10 to the negative 9 by 100? Like, do you want us to convert it to parts?
No.
Okay.
No, you don't have to. You don't have to do that, but you have to be familiar with expressing things in terms of percent, parts per million, parts per billion, parts per trillion, and then just be able to interconvert.
Okay.
And so this is just an exercise in getting more comfortable with different units. You know, they're all the same. The percent is a part per hundred. You know, and then a part per million, part per billion, we handle them all the same. So to convert from a percent to a fractional form, to reconvert from fractional form or decimal form back to percent, you know. And the same thing, we could go fractional form to part per billion and then reconvert that into decimal, or we convert it into decimal or convert it back into whatever. And so you don't have to do this. You could just go ahead and use this. You're going to get the exact same answer because all these are the same ratio. Because all these are an intensive property. Intensive properties, it doesn't depend on if you have 100, a billion, or trillion, you're going to get the same ratio. Does that make sense? And so it's independent of the amount. But to make it more visually appealing, I'm just going to do this. I'm going to say it's 271 H2O18 H2 molecules for every 10 trillion waters. So if I have 10 trillion waters, I'm only going to have 271 of those be this. So that's 10, what is that, 10 million, 10 billion, 10 trillion. All right, and so that's it. We want to know how many did we consume. Do you think you consumed 10 trillion water molecules in that cup? You think you consume 10 trillion. If you consume 10 trillion water molecules, then you just had 271 of the heavy ones, the heaviest ones. But it turns out you consume much more than this, because a mole of water is 18 milliliters. And so this is more than 10 times that. And a mole is about a trillion trillion. A trillion trillion would be 10 to the 24. So we're close to a trillion trillion. And so maybe we consumed quite a bit more. And so let's figure out how many we consumed here. That would be so what we're going to do is I'm going to stop the calculation here and then figure out how many water molecules we have in 250 milliliters of water. So it's going to be 250 milliliters of water divided by 18.02 times 6.022 times 10 to the 23rd. And you had 8 trillion water molecules. And so this is going to be about 8.35 times 10 to the 24th molecules. And then we're going to do times 271 divided by 10 trillion. And it turns out that you've actually consumed quite a lot. You consumed 2.26 times 10 to the 14th H2O18 H2 molecules. So how many is that? That's 226 trillion water of these water molecules. 226 trillion of these H2O18 H2. Could you taste those? You just had 200 trillion of them. Could you taste them? No, probably didn't even register. Seems like a lot, but it's not really all that much. In fact, probably it's so hard to comprehend these because they're so small. And then, so maybe what we'll do here is, figure out how much in U and how much in gram you consumed. So could you figure out how much in U you consumed? Well, we know how much that weighs. Did you write this down? How much does the H2O2, H2O18 H2 weigh? It weighs 22.027364 U per H2O18 H2 molecule. So did somebody calculate the mass? .266. That was the calculation earlier. What did I just calculate? 2.26. Yeah. I didn't carry the extra 6 because I'm just going to round this to 2 sig figs eventually. So this 6 is going to be dropped. So even if I carried that extra 6, it's going to be dropped. So did somebody get that calculation? So again, you didn't have to do all this stuff down here. Let me highlight it. We could have just left this as percent, this last conversion factor. And so I'll write here, or, so if I left this as a percent, it was 2.71 times 10 to the minus 9 H2O18 H2 out of 100 H2O. So the only thing that was necessary is this one. So what did you get for the mass in U? You should just retain the digits in your calculator times rather than round them off, if possible. .99 times 10 to the 15 U. Is that what you guys got? Okay, good. All right, well, U I'm not that familiar with, but I'm familiar with grams. And so I need the relationship between U and grams. So we're going to derive the relationship. And we need the definition of the U. How is the U defined? Is there something that weighs exactly 1 U? Maybe they're going to come up with something, you know, some kind of physical, maybe electrical or magnetic interaction that gives that same force on a balance. But for right now, what is a U defined as? Not 1 U, it's 12 U. That's correct. 12 U is defined as what? The mass of 1 carbon-12 atom or nuclide. And so this is the definition of the U. What is the definition of the mole? Definition of the mole? You have a mic? Yeah. It's the number of atoms in 1 gram of, not 1 gram. It's going to be in exactly 12 grams of carbon-12, right? And that number we call a mole, and it's equal to Avogadro's number, and so bang. And so, in other words, this, there are going to be 6.022 carbon-12 atoms in a mole of carbon-12. And a mole of carbon-12 is exactly 12 grams of carbon-12. And so if we multiply these 3 things together, this is the definition of the mole here. And then use some dimensional analysis, we'll be able to figure out the relationship between U and gram. So let's go ahead and cancel out the units. So carbon-12 atoms cancel out here. Mole of carbon-12 cancels out here. 12 cancels out here. And this carbon-12 cancels out because this is U of carbon-12. And so I should write that here, U of carbon-12. And so now carbon-12 is eliminated from this. And all we're left with is U in grams and 6.022 times 10 to the 23rd. Oops, I forgot that. 6.022 times 10 to the 23rd. So 1 gram is equivalent to 6.022 times 10 to the 23rd U. Have you seen this conversion factor? No, you don't see this conversion factor because they invert it. And so take 6.022 times 10 to the 23rd and flip it upside down. And we get this. We get that 1 U is equivalent to 1.6605 times 10 to the minus 24 grams. Oops. Did I get that right? Yeah. This is the conversion factor in our book. 1 U is equivalent to 1.66 times 10 to the minus 24 grams. Which one's easier to remember? They're both the same. Which one's easier to remember? The top one. So if I were to remember one, I'd remember the top one. It's very easy to remember. And so let's go back to the previous problem. In this problem, I'm going to take my 4.99 times 10 to the 15 U, and then I'm going to convert that into grams. And so 1 gram is equivalent to an Avogadro's number worth of U. And so let's see how many grams of H2 are the heaviest of the water molecules you consume. So 4.99 times 10 to the 15 divided by 6.022 times 10 to the 23rd gives us 8.28 times 10 to the minus 9 grams. All right, I'm going to use a metric prefix. I want to get a metric prefix that gets rid of 10 to the minus 9. What metric prefix is that? Nano. That's correct. So this is going to be 8.28 nanograms. Total. So although you probably drank 226 trillion of those heaviest water molecules, it only amounted to 8.28 nanograms, which is barely anything, compared to about 250 grams of water. And so it's very little. Huge number of molecules, but very little water. All right, so we need to get the correct number of sig figs. So let's answer this. This is going to be 2.3 times 10 to the 14. .3 times 10 to the 14 molecules, which is equivalent to 5.0 times 10 to the 15 U. Which is equivalent to 8.3 nanograms. So this would be equivalent to 230 trillion. And this would be equivalent to what? 12. I don't know. 5,000 trillion. Just different ways of expressing the same number. All right. All right, any questions on this calculation? All right, we're going to start the new chapter, but I only have 2 minutes. And so what I want to do is I just want to tell you what you know, the next chapter deals with compounds, so we're going to have some nomenclature. And so I want to get you started on memorizing some polyatomic anions. And so can you start working on memorizing these?
Is there a page in the textbook where these are all listed?
Some, yeah. It's going to be in chapter 3. I'll tell you the page. I don't have the page number off the top of my head. But there are certain ones you have to memorize on the 8 anions. So memorize these. Borate. Does anybody know the formula for borate? BO3 3 minus. Silicate. SiO4 4 minus. Chromate. CrO4 2 minus. Dichromate. Yeah, Cr2 CR2O7 2 minus. Permanganate. Yeah. MnO4 minus. What else? Oops. Oxalate. C2O4 2 minus. Correct. Acetate. Yeah, C2H3O2 minus. And then there's some other 8s that aren't as common. I might have missed one or two, but here there are some other 8s in the book. So for example, cyanate. And thiocyanate.
I'm sorry, for dichromate, is that O7?
O7, yeah. CR2O7. These ones you don't have to memorize. What other 8s? I think these are pretty good. So just get started on these 7 8s here. Yeah, dichromate CR2O7 2 minus. And then tomorrow we have lab, our first lab, but you don't need safety goggles for it. So we're just measuring water. We're not going to do the entire experiment. We're going to do part of it. I'll talk more about it tomorrow.